Welcome everybody. So as Matt said, I'm Wayne Weaver here at Michigan Technological University in the Upper Peninsula of Michigan. And so today I'm going to be talking about some work that we've been doing for quite a while. Today's presentation and material is just kind of a small glimpse into some larger bodies of work that have been ongoing here, both related to marine and aircraft systems, and then the tie-in with the using the very nice Typhoon HIL high fidelity hardware and system to do testing. So before I get started, I wanted to kind of give an acknowledgement and thanks to AFRL, NAVSEA, Sandia National Labs, and UDRI for their ongoing support in components, different components of this work and our program here at Michigan Tech. Let's see. So as a kind of a background motivation for the webinar, really what I'm going to try to focus on is just an introduction to the multi-physics approach in studying this problem. Many of us in power electronics and the electrical power area are very used to the electrical circuits, but the couplings and the tie-ins with the other physical phenomena in these systems is actually a lot more important than many people give credit. So that's what I wanted to focus on. So the coupling phenomena, mostly I'm going to be looking at electrical and thermal, and of course there are some mechanical issues in there as well. And again, what we're going to be doing is looking at some of the small the analysis techniques, particularly where they focus in on limit cycle behaviors in a pulse network, and the metrics that hopefully, if not already figured out, is going to come out of some of this work for future designs. Okay. So the agenda, what I want to do today, is introduce this pulse load stability, which I have a paper currently published that I'll give you a reference to. Start looking at the electrothermal mechanical coupling, talk about some of the reduced order modeling and the reasons behind. We're kind of moving to some reduced order models, at least in the first step, to get started with this work. And then mix in some elements of not just the generic differential equation modeling, but how I've adapted those models to be used in the Typhoon HIL. And then kind of give you a brief live demo and some examples of the systems that are running live on my desktop and on my workspace here in my office. So just as a start, so generic, I'm going to focus in on just the electrical components and show you sort of what the issues are with the pulse network and the systems that are under these sort of high stress, sort of high demand loads, and some traditional the issues that are involved with constant power issues. So I'm going to focus in on just a very simple circuit, a boost converter with a passive resistive load and also an active constant power or a time varying nonlinear load. So potentially, the load on this system could be almost any function, but of most interest is some sort of PWM signal that we're going to get started on looking at. And that's PWM signal is representative of a lot of new loads that are going to come on to the aircraft and marine systems that are starting to be of interest and populate the systems today. So in future work and some ongoing other work that we have here at Michigan Tech, we're looking at many pulses on the system, but for today's presentation, I'm just going to focus on one pulse and how that disrupts the system and how that actually affects stability. So there's lots of small signal methods. Pick your favorite to analyze the stability of the system. For example, if I take the differential equations, the nonlinear differential equations of that boost converter, and I can linearize it into state space form and come up with a characteristic equation, or in another way of saying it is finding the eigenvalues of the system. So what falls out of this for stability is that I will get an idea of what the power, the true constant power levels have to be. And what these numbers and these equations are telling me is that I need at least some level of damping in the system. There has to be some power, and there's a minimum amount of power that has to go to resistive damping in the electrical network to make this thing stable. Okay, so that's what that analysis tells me. Well, there's been lots of work in the past, 30 or 40 years actually, that's looking at these issues, for constant power stability criteria. And again, many techniques have been evolved and many standards have been written. One of the most famous ones is looking at the impedance criteria, much like what I just showed for the linearization. And what's falling out of that is things like Middlebrook. Gain and phase margins are also another version of this. And those have been used traditionally for quite a long time to drive the load impedance specifications of high demand systems. So looking at just a constant power, where do the impedances have to fall to guarantee a stable system? Now, of course, the big question is, what does stable mean? And in what context is a system stable? Another problem, in fact, this is actually a different problem, is that according to those nonlinear systems, you needed at least a minimum amount of damping, but you can also run into the opposite problem with too much damping in the system. So, for instance, looking back at a very simple RC or voltage resistive network, if on the top one here, if that resistive load is just a pure resistive variable resistor, and then the source impedance is the parabola, there's always an operating point. That resistive load line is always going to intersect the red line and give an operating point. Now, we may not be able to get the power, so the maximum power is going to be at the nose of that power curve, but is always going to have some operating point. But with active power electronics nowadays, we can demand a high power, which is basically a load line that's a vertical line, as shown on the bottom. And in fact, what can result is that I've got a demand for power that exceeds the maximum power deliverable by the system. And really, what this boils down to is it's too much damping in the system. So for this active type of power load, I'm going to have too much damping, and I'm not going to be able to deliver the power. So I'm going to run into both problems. I may not have enough damping, and I may have too much damping in the system. So how does this actually affect when I start looking at more complex loads? So many new loads and high demand loads that are being added to a lot of military systems, air, naval, and land, are really kind of pulse loads. Not really constant power. They'll be constant. They may be a constant power for a pulse width, but are only on for certain periods of time over certain frequencies. And in fact, might come in bursts or may come in groups of pulses. So we're going to stick to just a simple PWM sort of pulse power characteristic. And what this really represents is a lot of new systems like radars, rail guns, lasers, C-whips, and EMALs that are going on newer aircraft and naval vessels. So previous literature, all those analysis techniques that I was showing before, Middlebrook, linearization, eigenvalues, those might tell you something about when the power is on or the power is off, but things get a little bit less clear, especially for stability, when you look at the entire signal. This is a very large signal, nonlinear system, and so there's limited tools to be able to judge the stability of this sort of load. So what I mean here is that if I go back to this simple boost converter network, and for that nonlinear load here, if I hammer that with a pulse load demand, what I might get is something that looks like on the bottom. So the pulse is actually that current source is giving me a pulse of power, and that's going to ring the voltage on that capacitor, that bus, essentially. So it's going to ring when the pulse is high, and shown here is might damp out. So when the pulse is high, by all linear methods, with the example shown here, that system is unstable. Okay, and you could do the analysis when the pulse is on. The eigenvalues would be in the right half plane, real parts of them, or any of the other favorite methods to analyze the stability. But that system would say it's unstable, and by many accounts, that would be the end of the story for a lot of previous approaches to the design. So if I had a pulse load that gives a power that shows by linear methods that is unstable, the whole system is just kind of thrown out and not considered. But if you look at that time domain signal, and what emerges is really kind of a limit cycle, where maybe during the off periods, the system becomes stable again. I've got enough damping that during an off period, the oscillations damp out, my voltages don't increase to some unmanageable levels, and the system becomes feasible. So overall, the system isn't really stable, isn't really unstable. In fact, it's kind of what we've settled down to a term that we've called meta-stable. It's not really well-behaved system, but with proper design approaches, you can actually guarantee some level of operation as long as you're willing to maybe let the voltage on the bus vary a little bit, and of course the levels are completely within the scope of the design on how much that voltage variations are allowed to wander. So how do you analyze this sort of system? That's the question. Linear methods, even periodic methods like flow-K, all sort of break down for this sort of analysis. Flow-K gets you a little bit closer than just straight eigenvalues or some other methods, but still, flow-K is essentially a periodic linearized method. So what we've taken here, the approach that we've taken is we've started to go back and looked at the core energy approach to a system, and in a lot of ways, especially when you start looking at the coupled network, what the actual thermodynamics of the system are going to be. So the Hamiltonian of the system looks at all the energy in the system, stored, kinetic, and potential, and we start looking at the time derivatives and getting the energy and the power flows in the network. Okay, so over some cycle, which would be the pulse cycle, what energy is generated and what energy is dissipated. So we call those the generators and the dissipators of the system. Of course, for this simple network, for that boost converter, those are quite well defined. You've got both the source and, in fact, that power element there becomes a generator. It gets generating entropy in the system. And then I've got the dissipators, all those resistive damping terms that we had before. So for stability, for an overall limit cycle, stability case, over some period of time, over some limit cycle horizon, we need the dissipators to be bigger than the generators. And essentially, in a nutshell, that's the approach that we've taken for looking at these pulse power networks. And of course, it does get a little bit more complicated to actually implement that. And in fact, this is a paper that we have published. I put a reference to it on the bottom of this slide if you're interested in reading more. You can use that Hamiltonian surface shaping power flow approach, looking at the generators and dissipators, and actually map out. In fact, the top right here shows a map of a simple pulse network showing stability margins. So some interesting results came from this work, looking at this map, this plateau here that you can see on this mapping up along the top where it looks like a little table. That's actually the power levels that are linear models. So if the power levels are small enough, it's always stable, but as the power levels get bigger, stability drops off, but I'm still able to operate. So in that work, we did both HIL and hardware. In fact, this is on the bottom here is a scope image of the hardware results that we did, and we're able to confirm a lot of the results that we were able to see. Now, a lot of that work looked at the dissipators in the system. So the examples from that prior work were just looking at an electrical network, but in a larger electro-thermal mechanical system, we actually could get a lot more damping effects out of some coupling that might be going on. So the whole story needs to be looked at in the context of a bigger system. So mechanical coupling, mechanical couples to electrical systems, usually through motors and pumps and prime movers. The electrical system delivers power to a load. That load is going to generate heat. The heat in turn changes the efficiency of the electrical network, which changes a damping essentially, and I'll get more into that. But the thermal system also needs to be cooled to maintain a temperature levels, usually through some sort of pump, cooling loop, and then the thermal system can actually go back and affect mechanical. So all three of these types of domains are interconnected and are coupled. In fact, we can even start looking at more domains, a chemical domain and other things too, but for all intents and purposes, we'll just stick to these three domains right now. So the model of the system we're going to look at is, it's going to have prime movers, maybe have different distribution systems, power networks, power electronics, storage devices, and all sorts of power loads. But for our study, what we want to do is start looking at how that constant power load affects the electrical network stability issues. Okay, so all the domains are going to be coupled, and then looking back at the voltage levels of the electrical network. I'm a power electronic guy, so I'm going to look at the electrical system. So there's two primary mechanisms. There's, again, as we mentioned before, there may not be enough damping, and there might be too much damping that gets you into trouble for that voltage levels. So what's going to happen, what we've seen, what's come out of this work, is that a lot of the thermal coupling to the electrical network shows that low temperatures in the system really give you a good efficiency, but don't provide enough damping, may not provide enough damping to maintain a stable system. But high temperatures, on the other hand, might be too much damping. So that plays right into the stability issues. So there's a range of optimal temperatures that might need to be defined in a large coupled system that you under study. So what I'm going to show here, and of course we can go to the nth degree of detail in a model, but what I'm going to show here is some of the simple model networks that we developed, and just to use as a starting point for our first studies. And what I'm going to present is also, a couple of assumptions. For one, I'm not going to include any storage controls. I'm just purely want to look at the open loop behavior of the system. So no feedback loops. Haven't designed, these don't include any design feedback loops, and there's no energy storage in the system. So just look pure open loop behavior. And also, you just try to simplify things a little bit more. Gonna ignore some of the prime mover dynamics, turbines and reciprocating engines. Look at all DC power, and energy storage are ignored. So this is essentially the circuit that we're going to look at. So there's a source of the system that's kind of emulating the generator. There's a power distribution bus. There's a pump load system that circulates a cooling reservoir, cools the pulse power load here. This is exactly the same model that we showed before. So a nonlinear pulse load. But the coupling now is that we've introduced a variable impedance that's thermally dependent. So there's a coupling between the temperature of the thermal system or of the load or the weapon, and that's going to add or take away damping out of the electrical network. So the assumption also is that these pulse loads are usually not very efficient. So there's a certain percent, usually in the 80% of that pulse load actually is going to be dumped into heat. So about 80 for our models here, 80% of the pulse load of the load power is dumped into heat. That's going to heat up the element here, and then we have a cooling loop to cool it off. And that temperature of the cooling loop of that TC is going to change that resistive element in the electrical network. And if you're interested, here's the differential equations that we could use to describe. So these differential equation models often come in pretty handy for analytic analysis and also at least getting a start for that Hamiltonian analysis and determination of stability points.